Okay, so since we're really finished with chapter 6, or sorry, finished with chapter 5, we're starting chapter 6. Rather than just kind of going through the basics, I want to do a more in-depth problem, at least two in-depth problems that are on your chapter 6 homework. And I think these will be helpful for you as you do the homework. Chapter 6 has a lot of problems that can get kind of tricky if you're not watching them. And it really combines everything we're talking about. So setting up a problem in terms of forces. Oops, just a minute. Okay. Oh, okay, that makes sense. Sorry. Okay, now I know what's going on. Okay, so now we're back at starting. Okay, 6.4. This is 6.47. And in this problem, if you read it, you basically have, certainly not going to draw it well, but you have a truck, going up an incline. Make that not as shallow. And it's not a rough incline, but you basically have a truck, carrying a pretty heavy load. This is why I don't draw drawings that well. Maybe something like that. That's reasonable. Okay, so we got the truck and we got the load, and they're moving and this is a 15-degree angle. I'm going to use numbers in the book. Everyone's numbers will be slightly different. And we know that the mass and the truck and the load together makes a mass of 7,500 kilograms. Again, this is in the textbook. Everyone's numbers will be different, but we're moving at a steady, typically we like the velocity to be on the object. So we're moving at a steady 15 meters per second. And what happens is the catastrophic load falls, and so evidently, right, the pretty heavy load, so you have to be pushing hard on the gas to get this thing to move up. Well, the load falls off. Yikes. Right, and evidently when the load falls off, the truck has a recorded right, sorry. The truck itself has a recorded acceleration of 1.5 meters per second squared. Not because the load is pushing on the truck, the load is falling off. And if you can imagine, like we were pushing hard on the gas to move up this heavy object. Once the heavy object accidentally falls off, our foot is still on the gas, and so we have this large acceleration. So we're asked to find the mass of the truck. And it's a smooth incline, so no rolling friction and just enough static friction to keep us rolling. So we're not having friction in this problem. Okay, so this is a good problem to set up. And if I were you, if you're watching this video later, certainly pause the video and try to do it yourself before going through it. In here, we'll certainly just kind of talk about it. There's two different situations here. And each of them have their own free body diagram. And so how do we do this? What's the diagram look like on the first part? Well, when you're going up or down inclines, it's very helpful to use a tilted axis, a tilted coordinate system where one of the axes is the same, one of the axes is the exact same lateral to the incline, and the other one is, perpendicular to the incline. So this for situation, let's see how we want to indicate this. So this is situation 1, right? And then I'll have a diagram for situation 2. So situation 1, there's a force up the incline from the car. So let's call that F sub T. There we go. There's some force that the truck is exerting right, there's some force that the truck is exerting to keep us from sliding down the incline. Because if it's a smooth incline, what's going to happen is we're just going to roll down. And so there has to be that force up the incline. We got downward gravity. Now gravity is vertically downward, and I'm going to call it mg, right? Because in chapter 6 we learned that the gravitational force is proportional to the mass of the object and the gravitational free fall constant. And then also we got a normal force up the y-axis. And the other thing this problem mentions is that it's a steady 15 meters per second before the load drops. And so we've got F net equals 0. And so this is a great free body diagram for the first problem. What about in the second problem? Well, when the load drops, I mean, our mass, as you can tell, it's going to greatly decrease, but the force is the same. And so I'll draw this, say, kind of below here. I would argue use the same axis. Use the same coordinate system. I mean, you're free to use whatever coordinate system you like, but these are all this axis, and it's, you know, not really, a little exaggerated for clarity, but all of these, it's the standard XY plane that's been, everything's been rotated by 15 degrees. So I'll delete that. What's the free body diagram look like after the load fell? Well, the force is still the same. The force of the truck is still the same. It's really the, you know, when you talk about this, the force of the truck is really, you know, you press on the accelerator, that causes the pistons to, you know, turn faster, which causes the gears to cause the tires to move, all this stuff. But the gravity force is much lower. Maybe m sub t g. Maybe up here, it might be more helpful instead of little m times g in this free body diagram at the top, replace it and just call it capital M times g. Let me clean that up. Oops. I think that's more helpful. So cap M is the mass of them when they're together. And we know that cap M is 7,500, but we're trying to find little m, which is the mass of just the truck. Maybe little m sub t, right? And then, you know, define your symbol. Cap M is 7,500 kilograms. We're trying to find the mass of the truck, right? Theta is 15 degrees. That's about all we know. And this is smooth. Okay, so smaller normal force. So it's technically a different normal force. Might even call this a capital N for big normal force, but we don't need the normal forces. But in this bottom free body diagram, we have a net force. It is a non-zero net force. It points up in the direction of F sub t. So that's the setup for the free body diagrams. Always use these sort of tilted axes when you're handling an object sliding up or down along an incline. Banked curves, if it's taking a banked curve, it's a different story. We talked about that in chapter 8. Okay, so with that, this is a good pictorial representation, right? We're modeling, of course, the truck as a particle, you know, and doing things as correctly in the book as we can. I mean, you know, if you have someone who's drawing a picture like this, right, drawing the load, and just need to get better at just drawing a truck. Let's load. You know, if they draw something like this, where that's reasonable for a tractor trailer, right? If they draw like gravity down here, and normal force, you know, up here, and the force of the truck, like right here. I mean, again, drawing forces in different locations can be confusing. And that's why the free body diagram is meant to be very organized, and all you see the forces all in one spot, and more or less their relative sizes. Now, how do you know what their relative sizes are? That kind of comes with practice. But let's sum the forces here. Okay, let's do the first free body diagram, because these are separate situations, one with the load and one without. So let's sum the forces in both the directions for the first part. Okay, this is the skill that we learn in chapter 6 of taking a free body diagram and being able to write it as an equation, or really a pair of equations in the x and the y direction. Making sure to monitor the plus signs and the minus signs and deciding what it's equal to. Okay, so in looking at this downward gravitational force, this downward gravity force, this is the 15 degrees right here. Okay, that 15 degrees is with respect to the vertical. And so this is going to make the x direction be, you got the force of the truck. It's going to be positive force of the truck. And it's going to be minus the big mass, it's the 7,500 times the free fall constant, but it's the x component of this vector. And what's weird is that we think of this as the x component of gravity, but x is not horizontal. And so this actually ends up being mg sine of 15 for the units, or for the values that are given in the textbook. 15 degrees. Everyone's going to have slightly different numbers. Okay. Just a minute. Yeah, just 1 through 4. Yeah, I'm just looking at a couple other things in chat. Yeah, the test is only chapters 1 through 4. Okay. Right. So in continuing with this, sorry, I was just checking real quick some of the chats. Okay, so now that we have, in going back to this problem, set this, what this equals 0. And so in principle, we can find the force of the truck. The forces in the y direction aren't really relevant, but they're still worth doing. In fact, that's going to bother me. I will make it a cap n, just because there's two normal forces in this problem and they're different. So here we have cap n, or maybe plus n, plus capital N, minus capital mg cosine of 15 degrees also equals 0. So that's how you sum the forces in this free body diagram for the first example, where F net is 0. We have this truck force, this relatively unknown truck force that we're trying to find and use for the bottom problem. So this is how you find the truck force. So evidently the truck force is just, you know, it's for the book, it's going to be 7,500 times 9.8. I'm not going to have nearly enough room. Oops. Let me move this. Let's see. Can we move these? Yeah, right, just so I have more room. Okay, so force of the truck equals 7,500 times 9.8 times sine of 15 degrees, and that's newtons. Whatever that is, sine of 15 is pretty small. You know, 7,500 times 9.8 is about 73.8 or something like that. So, or 7,380 or something like that. So that's how you find the force of the truck. Now, once you have the force of the truck, you do the second problem. And the second problem, it's the sum of the forces in each of the, myself enough space. Yeah, I should have enough space. Yeah, the sum of the forces are a little different. It's this in the x direction, it's the same force of the truck in the positive direction, but now it's minus a smaller mass of the truck, not just the combined mass, g, same sine of 15, but now that's going to equal 15 degrees. It's going to equal the mass of the truck times that acceleration, because the F net points along the x direction. And in the y direction, it's little n minus little mg cosine 15, that equals 0. Once again, not relevant, but still, but still helpful to find, because we will need those in friction problems later. Okay, and so now we can work to find the mass, because we're trying to, this problem, we're trying to find the mass of the truck. And so once you know the force of the truck from the first part, then you can find the mass of the truck in the second part. And so it looks to me like the mass, I'm not going to do the calculation, it's going to be different for everybody, but the mass, because we know the acceleration, that's 1.5. We know g, we know sine 15, f of the fourth of the truck found in the first part. Yeah, and so it ends up being, I see, yeah, it ends up being that the mass of the truck is equal to the force of the truck. I'm trying to solve all this at once. Certainly do numbers if you're more comfortable. Force of the truck. So if I'm taking this thing and putting it over to this side, right? And then factoring out everything and dividing to solve for m. So this is, I say g sine 15 plus a. I mean, which f itself was cap mg times sine of 15. So I'm not sure if you can really simplify that, but certainly that ends up being the answer. So it's capital M g sine of 15 divided by just g sine of 15. There's got to be a way to factor that out. Plus a. Oh yeah, I know what to do. Yeah, this is a technique that we often don't use, but you can factor out, obviously, how do you factor out a g sine of 15 from the denominator? Well, that is just, g sine of 15, you just take it out of the first thing, 1, and then you pull it out from the denominator, the other thing. Yeah, so that can cancel that, and you get a more elegant answer of m over parentheses 1 plus a over g sine 15. I'm not sure how helpful that is, but that is technically the answer in terms of everything that you were given. All right, this looks pretty good. Any questions or comments on this problem? Here's another practice problem. Also happens to be a homework question related to chapter 6. And it's a little bit more difficult. And I think it's there's no numbers in it. And so it's kind of symbolic manipulation. A lot of times folks are, get concerned about doing problems like that with symbolic manipulation, but it's good practice, and let's try it out. So similar to the truck problem, but with no numbers, we have a block. This is length L, this is height H, and we have a block at the very top of this incline, right? That's released from rest. And it's a very small coefficient of friction, so this is rough, but it's not rough enough to where the static friction takes over. So coefficient of kinetic friction is what describes the friction force. Okay, really quickly, some just-in-time reviewing. We've got the expression for the kinetic friction force, that is its magnitude, is proportional to the normal force. These are, this is a common thing you see, but they're perpendicular, right? So if you take the, and what does that mean? You take the dot product between these two vectors, you should get 0. Because they're perpendicular, and F will always be opposite. So F of K is always opposite the direction of motion, right? And so we got cross product between an object kinetic friction force and its velocity is 0, not the dot product, cross product. It's helpful to think of vectors in terms of these sorts of relationships, even if they're parallel or perpendicular. So, and their dot product is less than 0, right? So that's the direction of the kinetic friction force, right? Remember last time we talked about Newton's second law in terms of net force and acceleration, right? Both of these give us an expression that on the surface, the velocity and the friction force have to be anti-parallel, as opposed to F net and acceleration, which have to be parallel. So I don't want to get into lecture about this stuff. I want to do the problem, but this is just a brief review. That coefficient of kinetic friction tends to be around 1, less than 1. The slippier, the more slippery the surface. Right. And yeah, an issue with this example is that we don't have angle. Technically, you can make up an angle theta, but that, yeah, you'll see what happens where we can work with theta, but we're going to eventually need to convert back. Because what we want to do is we start off at rest. So our initial velocity is 0, so we'll call V0, 0. Work in a typical coordinate system. And we want to find an expression for the speed at the bottom, V1, right? So obviously we're going to be accelerating down the incline. And so now let's draw a free body diagram. This one's going to look a little different from that truck problem. That looks good. X and Y. That. Now, what are the forces in this example? Well, gravity. Now we don't even know the mass of the object. You can just call it m if you like. But we don't even know the mass of the object, and that m. So we're going to have m that points vertically downward as usual, or gravity, mg. And by the way, if we know we're accelerating down and to the right, that activates Newton's second law, excuse me, and so we know that F net also points to the right. And normal force, it's always, normal has like the meaning of more like perpendicular. We got N right there. And then we have a backwards friction force. If we're moving down and to the right, then our friction force has to point up and to the left. And so that relatively small kinetic friction force. So that's a perfectly good free body diagram describing the motion of this particle that slides down a moderately rough surface. It's smooth enough to where it doesn't like slip, like it's not like stuck. But there is a certain amount of friction. Okay. So how do we set up these equations? And ultimately what we're trying to find is V1, right? Well, this is again where we connect the forces. The whole point of the forces is to find the acceleration. That's what Newton's laws are all about. That's what Newton's second law is. If you know all the forces acting on an object, you can determine how its motion changes. All those forces working with and competing against one another are what determines the object's change in motion. So anyway, let's see what we've got now. So you need to use kinematics to find V1, right? This is just something from chapter 2. So it's like V1 squared equals V initial squared plus 2a sub x. I guess x is the axis times delta x. That's the equation that you would technically use. Delta x is really just the length of the thing. So that's L, right? Our initial velocity is 0, so we can cancel that out. So if you look, it's just V1 equals square root of 2a. Oops, I'm kind of coming in on the other part, aren't I? It's fine. Square root 2a times L. And all we need to do is find an expression for acceleration, then we'll be done. Okay, I'm going to erase the part on the right. So now that we got really what we're trying to find, we just need to find acceleration. Now, again, the point of these examples is to show you how you find acceleration. The way to find acceleration is use Newton's laws. Sum the forces in each of the directions and find a way to get A. So let's sum the forces. When I do these parentheses x, this really means like sum of the forces in the x direction. It's faster. And sum in the y direction. It may be that we need both these equations, not. So in looking at this free body diagram, how are we going to approach this? It might be helpful for now just to use an angle, but the problem doesn't ask for an angle. Like if you plug in theta for the answer on Mastering Physics, you're not going to get it. You're going to get instead something like, use H and L. Well, we'll get to that. We'll cross that bridge when we get there. Let's sum the forces for now. So in the x direction, what have we got? Well, typically y direction is easier to work with. In the y direction, we've got normal force minus mg cosine theta equals 0. And when you're on a surface, this is a pretty standard equation actually, unless there's other forces in the y direction, like a rope at an incline or something. But so we know that the normal force is mg cosine theta. What about in the x direction? Technically this is plus n. In the in the x direction, it's going to be, and follow me here, it's going to be plus mg sine of theta minus the kinetic friction force. That's going to equal plus m times a. Now that we have this pair of equations, the next thing to do is use what we can to solve for a. And kind of tricky because it might seem that we're just doing random numbers, but what are we looking for? This question is looking for a in terms of, say, g, the height of the incline, the length of the incline, and mu. I don't remember if it says mu or mu sub k, but that's all we're looking at for it, and we don't even have a lot of those. So the big connector between these two equations when you've got friction is that kinetic friction, like I said, is equal to mu sub k times n. So if you look at n, right, the normal force is equal to mg cos theta. Oops. So when you add a coefficient, then the kinetic friction force is just it's just mu times mg cos theta. So I'll write that down here, just turning that arrow at the bottom of that friction equation just back into an equal sign. So this equals mu sub k mg cos theta. And you see that once you do that, you can actually plug it back into x, right? And that that becomes plus mg sine of theta, minus mu sub k mg cosine theta equals plus ma. So a couple things to notice about this example. First, the masses cancel. And that turns out to be true in general. If you have only gravity, normal, and this basic friction force, then the mass always cancels. That's the first time we see, well, maybe second time, that we see where the motion is independent of the mass. And so you take a 1 kilogram block versus like a 10 kilogram heavy box. If they both slide down the same incline with the same coefficient of friction, the heavier one will reach there at the same time with the same speed as the lighter one. There's probably quick check questions out there that is these Zoom poll type questions where you might be confronted with that later, but yeah, it's easy to confuse that. So the mass cancels. So I'll just write a slash through all of those. And then there's your expression for A. It's just g sine theta minus mu sub k g cosine theta. I'm repeating, but minus mu sub k g cosine theta. So you might think that we're pretty much done, and we kind of are. We're almost done, but we need an expressions for sine theta and cosine theta in terms of h and L, the height of the incline and the length. So that just makes us go back to basic right triangle geometry and ask ourselves, okay, if we got a right triangle here, hypotenuse is L, one side is H, and the corner of the other side angle is theta. What's sine of theta? This is the easy one. Sine is obviously defined as opposite over hypotenuse, and so this is H over L. But what about cosine theta? So that's cosine theta just by using the Pythagorean theorem. And it's a helpful skill to keep with you over these next chapters of how to find cosine of or sine of an angle without knowing the angle. That technique follows around a lot. And so with that, we can find our acceleration, and it's going to be something kind of strange. Well, not our acceleration. We're looking for our final speed. That's square root of 2AL, because that was the length of the thing. So you can plug that in, 2 times g sine theta minus mu sub k g cosine theta times L. Yeah, right? Yeah, all square rooted. And you put this into Mastering Physics after you're very proud of yourself for having worked all of it, and it's wrong. Okay, or at least Mastering Physics won't accept it. If I look at it, I say, well, that's actually correct, but we have to put these expressions for sine and cosine in terms of H and L to have that final answer. So we will actually have a square root inside a square root, a rare occurrence of that. And so If you replace the sine of theta with, h over L, replace the cosine with that square root over L, the L's cancel, and what we're left with is something like this. So I'm going to factor out the G, 2G. Oh, whoops. Oh, sorry. There's another equal sign there. It's just, oh, geez. Okay. It's fine. I'm going to get rid of that little equal sign. Banish it to the Zoom clipboard. Okay. Stuck there. All right. So this is the final answer. Will be square root. I'll leave the square root till the end just because it looks nicer. So it'd be 2G, and that would be sine of theta, which is h over L, but it's going to cancel with the L on the far end, so it'll be h. What about this other thing? Minus mu whether it's mu sub k or mu, I'm not sure. Square root L squared minus h squared. That is the thing that's square rooted. So there's a double square root you have to work with here. So that'll be fun for you to enter in one of those equation editors that they have for mastering physics. But that is the final answer for the velocity, for the impact speed as it slides down the incline. Notice how if it was a smooth incline, then the final speed would just be smooth. Then the final speed would be just square root 2gh. And so this makes sense because as the coefficient goes to 0, then obviously this second term in the parentheses goes to 0. What else? Let's look at some other limiting cases. As the height approaches the length, what happens to this? Well, no matter what the coefficient is, final speed would approach just 2gh, actually. Yeah. No, it wouldn't. It would be 2gl, excuse me, because the h's would cancel. So this isn't the best equation to do limiting cases with, but certainly there's plenty of opportunity for discussion here. Save that to whiteboard.